right, hi guys. So really enjoyed working on this today with you. So remember we talked about, optimization involves you looking at the entity that you're trying to maximize or minimize. You have to generate an equation of that thing that you're optimizing. And then you have to contextualize that equation to make it unique to this particular situation. You know, when you do this contextualizing, right, that's called incorporating the constraints of this particular problem. And in here, this constraint was that the fencing equaled 400, okay? So now we're going to do a different kind of optimization question here. What I want to do is look at question number 4. Which point on the graph of y equals root x is closest to the point 5 comma 0? And like I said, with many of these optimization questions, the minute you take the 30 seconds just to draw a diagram, it inevitably will save you a whole lot of heartache moving forward. And y equals root x is a nice kind of review of just some basic functions. It looks like this, right? Okay. And it's saying which point on the graph of y equals root x is closest to the point 5 comma 0. And there's 5 comma 0. So which point on this graph is closest to the point 5 comma 0? So my question that I want to ask you is, what are we optimizing? And optimizing means finding the minimum or the maximum of something. What are we trying to minimize? I think you'd agree that in a question like this, we want to minimize a distance. And in particular, we want to minimize the distance between a point that's on the graph of y equals root x and the point 5 comma 0. And the question is, right, where should that point be? So I'm just going to put a point here, right? That point is x comma y, right? Some point. The question is, what are the ordered pairs? What are the values of x and y that will minimize that distance d? Okay? So right away, you know that we're trying to minimize d. And the question then becomes d. Distance. How do I minimize distance? What do I do to minimize distance? Well, I first have to generate the equation for distance, the distance between x, y, and 5 comma 0. And I know that I have to generate an equation for distance because that's the thing that we're optimizing. And if you recall here, the distance formula, x minus 5 squared plus y minus 0 squared, or y squared. That's the thing that we're trying to minimize, okay? And I also want you to notice that when I look at this equation, we have to minimize d. We already look over here and say, well, ideally, I'd like to have just one variable over here. I have two variables, x and y, right? Similarly over here, look at this question, right? Our first equation, I had area is length times width. Not only were there two variables in this case, this equation was not contextually unique, but this step here, where we have a single dependent variable and a single independent variable, that's the world we live in, right? We'll deal with multiple independent variables next year in multivariable calculus, but the world we live in this year is a single dependent variable, a single independent variable. And that's not what we have right here. So when you look at this, is there a way that I can get rid of one of these independent variables? And maybe you'll say to yourself, well, let's see. If x comma y is always on this curve, maybe you'll make the connection that x comma y is just x comma root x, right? Because y is root x. And if this point is on this curve, this becomes, right, that root x becomes my y coordinate. And then when I incorporate that into the equation, I get this. D equals the square root of x minus 5 squared plus x, because if y is root x, squaring it gives you x, right? Now I'm ready to go ahead and try to minimize. I'm going to minimize distance. And so now I'm going to take the derivative. I'll take d prime, or I'll do dd by dx. And you have to be careful here, right? All that work that we did on making sure we have all our derivative rules correct, this is why. All to the negative 1/2, and then times derivative of the inner, 2 times x minus 5, right? Okay, now the thing is, I'm going to have to set this equal to 0, right? I'm going to have to set this equal to 0 to solve for first derivative critical points. And I'm looking at this, and my eyeball is clearly telling me that I could probably clean this up to make my life a whole lot easier. And I noticed today when we were doing some board work in class, let's do this first, 2 square root of x minus 5 squared plus 1. When will this equal 0? Okay. I noticed today in class there's a little bit of kind of stumbling with just some kind of basic fraction operations. So just be careful here, right? When we need to do the algebraic cleaning, as we do, just do it correctly. Take your time, just be careful. Notice I distributed the 2, it's right here. This 2 is down here, and I brought all this down low and made it the positive, all to the positive 1/2, right? It's the same thing. Okay, so let's see first derivative critical points. Any first derivative critical points, the first thing I'm going to look at is there any way that the denominator could equal 0, right? Is there any way that this entity could ever equal -1? The answer is no. So there are no points of non-differentiability. But then I have to ask myself, what about 2x minus 10? Could that equal 0? And x equals 5, okay? Here I want to talk about using the first derivative test for extrema versus the second derivative test for extrema, okay? So if I'm looking at the first derivative test for extrema, I'm going to have to end up plugging values of x into this. I wouldn't say it's a big fat pain in the butt. The other option is to use a second derivative test for extrema. And when I look at this, if I'm going to use a second derivative test for extrema, I have to take the derivative of this. So let me ask you, which one is going to be less of a pain? Taking the derivative of this to use the second derivative test for extrema, or use a first derivative number line and just plug in values of x into the first derivative? I am going to go with using the first derivative test for extrema, okay? So I'm going to make my number line over here. Here's my d prime number line. Here are my values for x. And the nice thing about optimization, like questions that are kind of word problems, we can incorporate kind of commonsensical domain restrictions, right? I think you'll agree here, for example, the x value is never going to be 0 or negative, right? I mean, just eyeballing, I know that I guess it could equal 0, but even eyeballing it, right, I clearly see that distance is going to be bigger. But I'm just going to make a reminder to myself that, I really don't care about values of x that are less than 0. And frankly, values of x less than 0 wouldn't even be relevant. So I'm just going to end that, close that number line at 0. And then here's 5, okay? And I'm going to plug in a value to the left of 5. I'm using the first derivative test for extrema. Remember that, because finding the second derivative is a big fat pain. I'm going to plug in 1 into the first derivative right here, right? When I plug in 1 into the first derivative, positive down low, negative up high, negative, negative, negative. I'll plug in a value like, 10 over here, okay? And positive, 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 positive. And if you look at this, take a look at this on analysis. By the first derivative test for extrema, d is minimized, okay? D, the distance, is minimized at x equals 5 by the first derivative test for extrema. Now, I'm going to make sure I answer the question, which point on the graph of y equals root x? Ah, very good. I am going to say that we didn't fully answer the question. The point has to be an ordered pair. So the point is 5, root 5. And if I wanted to go to my picture over here, I can go ahead and draw it. So really, it turns out that d is minimized at this point right here, which kind of makes sense, right? Because if you look at it, right, this becomes a straight kind of perpendicular distance, if you will. And we know that the distance between a line segment and a curve, actually delete that perpendicular statement. That's not always the case, so just delete that part. All right, so this should give you a good springboard from which you can try those 3 optimization questions that I put for homework. And I'll see you Monday. Goodbye.